Hello everyone. Today we'll study the tangent lines of space curve, the tangent plane of space surface, and approximation. First, we consider the tangent lines of space curve GARM in the following two types of equations: parametric equation and general equation. Case 1. The equation of a space curve GARM is a parametric equation where the three functions are all differentiable. M, x0, y0, z0 is a fixed point in the curve GARM, corresponding to parameter t0. M prime is a point in gamma near M with parameter t0 plus delta t. How to find the equation of tangent line at M? First, it's easy to get the equation of secant line M prime. When M prime approach M along this curve, the secant line will rotate around point M. The limit position of secant line is the tangent line at M, denominator divided by delta t, to obtain the following expression. When M prime approach M along the curve GARM, delta t will approach 0, 2. Then we get the tangent line of GARM at M. The vector t is the directional vector of tangent line and is called tangent vector. The plane which passes through the point M and is perpendicular to the tangent line is called the normal plane. Obviously, the normal vector of this plane is the directional vector. So the equation of the normal plane is as follows. Example 1. Find the equations of tangent line and the normal plane of the following space curve. Solution. At t equals 0, x, y, and z equal to 0, 1, and 2 respectively. That is, the tangent point is 0, 1, 2. Calculating the derivatives of xt, yt, and zt, and letting t be 0 to obtain the tangent vector capital T, which is 1, 2, 3. Based the tangent point and the tangent vector, we can get the equations of tangent line and normal plane as follow. Now we consider a special case. The curve is the intersection line of two cylinders, y equals yx, z equals zx. In fact, we regarded x as a parameter. Then the parameter equation of the curve is this kind. By the previous conclusion at M, the tangent vector is t, 1, y prime x0, z prime x0. So the equation of tangent line and the normal plane of the curve at point M are as follow. Now we considered the second case. The equation of the curve is the intersection line of two surfaces, f x y z equals 0 and g x y z equals 0. Suppose equations 1 determine two implicit functions, say y equals yx and z equals zx, represented still by the following equation 3. By the previous conclusion, the tangent vector is 1, y prime x0, z prime x0. So we need to calculate the derivatives of y and z with respect to x at point x0. Since the implicit functions yx and zx are determined by equations 1, substituting them into equations 1 is the following expressions. Taking the full derivative with respect to x on both sides of the equation 4, we have the following equations. Solve for dy dx, dz dx from the equation set 5 to obtain the tangent vector 1 dy dx dz dx or 1 y prime x0 z prime x0. When the tangent vector is obtained, the equations of tangent line and normal plane are easy to get. They are the expressions. Example 2. Find the equations of tangent line and normal plane of the following curve at P0. Solution. Taking the full derivative with respect to x on both sides of the equation, we have the following expressions. So, dy dx equals minus the root of 3 over 3. dz dx is 0. And the tangent vector t is this vector. So, the equation of the tangent line and the normal plane are these expressions. Now, we are going to discuss the tangent plane and the normal line of space surface. Two cases are considered: the implicit and explicit cases of the equations of space surface. Case 1. The equation of the surface is implicit, that is, it has the form fxyz equals 0. Let m0 be the surface, gamma be any curve on surface. Suppose the parametric equation of gamma is this form, where m corresponds to parameter t0, and the sum of these three terms is not to 0. Since the curve is on the surface fxyz equaling to 0, then xt, yt, zt satisfy the following equation. Taking the full derivative on both sides with respect to t and let t equal t0, we have the following expression. Denote n as this vector and note that t is the tangent vector of gamma at point m, so the equation can be rewritten as n dot t equaling to 0. That is, the vector n is perpendicular to t. Since the curve gamma is any curve on sigma and passes through m, and n dot t equals 0. Hence, these tangent lines are in the same plane. This plane is called the tangent plane, and the vector n, that is, the gradient of capital F, is called normal vector. In sum, the tangent plane is the plane formed by these lines. The normal line is perpendicular to the tangent plane, and n is the normal vector, also the directional vector of normal line. Since we know the normal vector and the tangent points, the equation of the tangent plane of the surface at M is this one, and the equation of the normal line is this equation. Example 3. Find the equations of the tangent plane and the normal line of this surface. Solution. Let capital F be this function. The three partials of capital F are as follows. So, the normal vector n at the point M is this vector, which is parallel to the vector 1, 0, 1. So, we can choose this vector as normal vector. Therefore, the equation of tangent plane and the normal line are as follows. Case 2. The equation of the surface is the form z equals fxy. Let capital F be this function. The three partials of capital F are as follows. So, the normal vector n at point M is this factor. Therefore, the equation of tangent plane at M is this one, or the form this one. The equation of normal line at M is this equation. The directional cosines of the normal vector n is the following terms. In sum, we have the following theorem. Theorem A. For surface fxyz equals 0, the equation of the tangent plane at M is this one. That is the form of this. In particular, for the surface z equals fxy, the equation of the tangent plane at M is this one. At last, we discuss the approximation of function. For single variable function fx, when it is differentiable at some point x0, then we have the first order approximation. Fx is approximately equal to fx0 plus f prime x0 dot x minus x0. Furthermore, if f has nth order derivative at x0, then we have the nth order approximation. Fx is approximately equal to the nth order Taylor polynomial. Similarly, for bivariate function fxy, we have the following first order approximation and the second order approximation. Moreover, this extends both to the nth order case and to functions of more than two variables. The details are best left to higher level books. For the first order approximation of fxy, in the view of geometry, we can use the tangent plane to approximately represent the surface near the points x0, y0, fx0, y0. Now, let's make a summary of this section. We studied the tangent lines and normal planes for space curves, and the tangent plane and normal lines for space surface. At last, we give the approximation of function and the geometry interpretation of the approximation. That's all. Thank you.